we have been discussing about this micromechanics system design in detail. So, today we will discuss about the energy methods of the elastic beam. In order to bring motivation behind this energy methods of this elastic beam, so let me introduce you to this energy harvesters. So, most of you might be aware about this energy harvesters. So, like let us take a kind of a simple piezoelectric structure. Of course, we will be discussing in detail about these piezoelectric structures. So, to give you a better understanding, these are kind of crystals. So, these crystals, when we try to apply a load, it gives an electrical biasing. Similarly, when I try to give an electrical biasing in one direction, I can get a displacement in the other direction. So, ideally, these kind of piezoelectric structures can be efficiently used as a sensor as well as an actuator. So, these piezoelectric structures, so ideally these are called as stacks. However, in order to overcome or in order to have a freestanding support to these piezoelectric structures, there is a concept which is available, which we called as unimorphing concept and bimorphing concept. So, as far as in this unimorphing concept is concerned, let us consider this as the piezoelectric structure, and this is a kind of a support structure. So, what happens is, when these piezoelectric gets deflected, the one way actuation is taken care in a forward stroke using a piezoelectric layer, and the return stroke is taken care by the supporting structure. So, in this particular case is concerned, so let us consider if I want to have it at a higher frequency of close to around few kilohertz or few kilohertz. So, ideally, so I need to have a capability in such a way that these support structures are capable enough in such a way that when such kind of actuations are happening, it should not create any kind of deflection or deformation to the structure. In fact, it should always closely work with the main structure, that we call it as an active structure, so that we can get a kind of a required displacement and as well as a required frequency what we are looking for. Now, in this particular case, as far as this morphing perspective point of view, it is classified into two, as I had mentioned earlier. So, one is called as a unimorphing, where we have a single support structure. In the case of a bimorphing, we have a two support structure in place, or in other words, equivalently with reference to an active structure, this should also contribute in such a way that the bonding is efficient enough, and then you get an appropriate deflection what we are working for. Now, let us take a simple case study where a piezoelectric bimorph is used as an energy harvester from a heat source. So, as far as in this particular case is concerned, these piezoelectric structures are like prone or actuated through a thermal system. So, what we see over here is there is a structure which is available, and the heating element. So, there is a resistor is there. So, the main function of the resistor is to give a kind of an actuation to the system, and then there is a kind of a magnetic field which is available, and there is a heat source which is there. So, with reference to the heat source, there is going to be a deflection in the magnetic field, and the deflection in the magnetic field is efficiently supported by the beam which is available over here. So, what does this beam does is, this beam will try to deflect back and forth in such a way that there is a kind of energy which will be generated, and these energies can be potentially used. Now, as far as in this particular case is concerned, if we try to look into the micromechanics perspective point of view, there is a beam, there is a structure, and then there is a kind of a heat source which is available over here. The heat source takes care of the overall actuation of the structure, so that we can see a kind of a deflection, and then the deflection which is adopted over here has a capability for harvesting the energy. Now, in this particular case, considering this as our main application, so let us discuss the micromechanism behind this particular process. So, we consider this as a kind of an energy method for elastic beam. So, statistically in indeterminate beam, so the unknown reaction, so if you try to look into it, so we have a kind of a structure. So, these structures has a force which is exerted in this direction. So, it is the fixed guide beam with the transverse load are guided at the end, and a statically indeterminate beam is present over here. So, such systems are basically solved using an energy method. So, the strain energy stored in the beam of length L is given by SC equals 0 to L sigma E by 2 AdX, which can be represented as 0 to L m squared by 2 EI dx, where m equals EI by 2 by dx square. Now, thus for a bar and a bar beam, Castigliano's theorem are defined. So, by considering this Castigliano's theorem, so the micromechanics, the Castigliano's first theorem, if the strain energy of a linearly elastic body is expressed in terms of its displacement, then the force at a point is equal to the partial derivative of the strain energy with respect to the displacement in the direction of the force at the point where the force is applied. So, mathematically, if we try to look into it, F equals dou S E of U by dou U. Similarly, when we try to consider the Castigliano's second theorem, if the strain energy of a linearly elastic body is expressed in terms of force, then the force at a point is equal to the partial derivative of the strain energy with respect to the force at the point where the displacement is considered in the direction of the displacement. So, mathematically we can represent it as U equals dou S E of F by dou F. Both the equations are general such that the force can be replaced by moment and the displacement can be replaced by rotation. So, the micromechanics thus to solve the intermediate beam in figure, so we have the following equations, that is x equals Fx equals R1x minus R2x equals 0, Fy equals R1y plus F equals 0, epsilon m2 equals minus m1 plus m2 plus Fl equals 0, and Ux equals L equals dou Se by dou R2x is the axial displacement. Now, though del by dou x equals dou SE by dou M2, which is the slope, and by implementing the Castigliano's second theorem, del equals dou SE by dou F. Thus, del equals M2 L squared by 2 EI plus 2 FL cube by 6 EI. So, M2 equals FL by 2. So, the del can be represented as minus FL cube by 4 EI plus FL cube by 3 EI, which is nothing but FL cube by 12 EI. So, this is the equation which is considered to solve the interdeterminate beam as shown in figure. So, this is a kind of a generalized equation which can be exhibited to form or to establish certain amount of parameters for, or we can establish such kind of equations for any kind of structures which has a similar domain. Now, let us take an example of a 2-axis micromirror which is supported by a serpentine beam. So, what do you mean by a serpentine beam? So, ideally when we try to talk about a beam, so till date we had discussed about a kind of a cantilever beam which exhibits. However, suppose I have a structure something like this. So, this is an inner structure and this is the outer structure. So, it is a kind of a concentric circle which exhibits. So, in this concentric circles we have 4 different supports. So, the main function of this support will be helpful for us to deflect this structure, especially let us consider this as structure A and this as structure B. So, the deflect structure A with different degrees of freedom. Now, based on the type of the degrees of freedom, so appropriately we can establish the beams for our required dimension. So, suppose if I am more interested for a movement or a manipulation only in one plane, then I can replace this beam with a spring. So, this spring will be capable enough in such a way that the structure can move only in one plane. In case if I am more interested to deflect the beam in this particular direction, so what I can establish is, so either I can go for a serpentine structure, or in a simple way I can have a kind of a cantilever kind of arrangement which will be capable enough to deflect the mirror based on our requirement or based on the capability. Okay. The other option would be, so the main advantage of going for this serpentine structure, so as mentioned over here, so the serpentine structure has a capability to precisely manipulate this base structure. So, not only with reference to degrees of freedom, it also has a good advantage in manipulating the beam based on the applications, or I would say based on the requirements. So, this is one advantage of this serpentine structure. So, let us take a simple case study where we are using a kind of a 2-axis mirror, 2-axis micro mirror. So, this micro mirror needs to be manipulated with a serpentine spring kind of structure. So, the serpentine structure is quantified as Q is in plane width and P is the length of the vertical beam and T is the out of plane thickness. Now, the strain energy of the system can be represented as SE equals L m squared by 2 EI dx, which is nothing but m squared L by 2 EI. So, by Castigliano's second theorem, the rotation is theta x equals L, which is dou SE by dou M, nothing but ML by EI. So, the total angular displacement for torque T equals M is the sum of all the so the total angular displacement for torque T equals M is the sum of all 6 beams. So, what are these 6 beams? 4 long beams plus 2 short beams. So, the angular stiffness constant is calculated as theta equals 2 Tp by EI plus 4 T 2P by EI, which is nothing but 10 Tp by EI. So, this K equals T by theta, which is nothing but EI by 10p. This is a kind of a generalized equation which is derived for a 2-axis micro mirror based on the requirements, and then the extension of this can be suitably applied for a certain amount of micro manipulation or a certain amount of micro deviation related applications. Okay. Now, let us see the next case. So, the next concept is called as a heterogeneous layered beam. So, as far as this heterogeneous layered beam is concerned, so we had discussed earlier about this unimorph and a bimorph concept. That is, the thought process is like we will be having an active layer. Over the active layer, we will be placing the kind of an active system, basically a kind of an active actuator on it. So, this active actuator activates and it will result in a certain amount of displacement. Now, in this particular displacement, like the shape memory alloy also participates, as well as the active layer will also participate. That is, the either it might be a bimorph layer or it might be an unimorph layer. Both will participate to create a certain amount of functionality. Here, I would like to introduce you to one particular case study. So, in this case study, like one of the key aspect with reference to this micro actuator, developing a micro actuator using a shape memory alloy, like shape memory alloy has a good amount of energy density. However, there is a major drawback with reference to the frequency which it is getting generated. So, in the case of piezoelectric structures, we can get a frequency in the order of few kilohertz. However, in the case of SMA based actuator, shape memory alloy based actuator, the frequency is restricted less than 15 hertz. In fact, there have been reports which says that, so people have attempted up to 25 hertz. So, 25 hertz is the max. However, in order to enhance the frequency as well as in order to use it for certain applications, what we can do is we can just integrate this kept-on polyimide along with the shape memory alloy structures, so that a one-way actuation is taken care by the shape memory alloy and the return stroke is taken care by the kept-on polyimide. So, this is a kind of structure which is fabricated over here. These are kind of heterogeneous layer. So, where are two different materials are two different layers are made to bring together. So, with reference to these two layers, so appropriately what it is observed is this has an efficient actuation, and appropriately establishing this actuation. So, we can have a control over the frequency as well as we can have the control over the actuation characteristics as well as the displacement characteristics. In fact, the interesting part of this system is this we will be discussing it in the in one of the module related to microfabrication, where we had fabricated kind of a Stewart platform using a SMA bimorph for some kind of optometronic applications. Now, in this particular case, like we can program the displacement based on our requirement. So, the programming is done by applying an appropriate strain to the system. So, by giving a strain to the system, so we can program the structure and then we can deform the structure what we are looking for. Now, in fact, this is a kind of a SMA based actuation which you can see over here. There is a hot plate which is available. This is a kind of flexible SMA thin film based structure. We are trying to place this SMA thin film based structure on a hot plate, where we could see it is a kind of, it is unfolded, it is getting unfolded because of the actuation of the heat. This unfolding is happening because of the actuation which is happening on the shape memory alloy. When the person tries to take it out, it again folds back. This folding back is happening because of the participation of the kept-on polyimide on this particular structure. So, like this is as mentioned in the overall video. So, this is a kind of an actuated bimorph. So, as fabricated, it has a curled structure. When we try to actuate it, that is when we try to supply a heat to it, it becomes straightens. So, when we try to take it back, so it comes back to its shape. Now, there are different phenomenon which exhibits over here. So, one of the phenomenon is something like, so there is no need to completely coat a kept-on polyimide on the SMA structure. So, we can have a limited layer, so that in such a way that we can have a control over the overall curvature as well as the overall dynamic as well as the frequency what we are working upon. So, in this particular case, so let us consider, so this is a beam length of L1 with a, in this case we have used a piezoelectric. However, we can also consider a SMA beam based on our requirement, and this is a kind of a Kapton polyimide structure which is integrated along with the shape memory alloy structure, so that the deflection in these structures can be appropriately taken care over here. Now, the overall configurations, the overall usage of this heterogeneous layer beam will be discussed in the next module. Let us consider a heterogeneous layer beam. So, as discussed in the last class, so we had discussed about this SMA bimorph based structures. So, in this SMA bimorph based structures, so what we are trying to do is we are trying to fabricate a bimorph, and we are trying to study the incorporation of this Kapton polymer towards the shape memory alloy, and we are also studying trying to analyze the actuation behavior and its characteristics. Now, this terminology is called as a heterogeneous layered beam or the heterogeneous layered structures. Now, as far as in this particular case is concerned, so we are considering this as a generalized system. So, in this generalized system, instead of a shape memory alloy, so we are considering a piezoelectric beam which is of length L, and on top of it we have a kind of a layer which is of L2, and the width 1 and width 2 are the different. So, E1 and E2, let us consider E1 and E2 be the Young's modulus, and T1 and T2 be the thickness of the beam, and Yn is the height of the neutral axis from the bottom of the bigger beam. The stresses are sigma equals E1 by P y minus Yn for y less than or equal to T1, and sigma 2 equals E by P y minus Yn for T1 less than y less than T1 plus T2. So, in pure bending, no axial force acts on the cross section. So, 0 to T1 equals sigma 1 W1 dy plus T1 plus T2 is sigma 2 W2 y, which is 0. So, the y power n is E1 A1 Y1 plus E2 A2 Y2 by E1 A1 plus E2 A2, where Y1 equals T1 by 2 and Y2 equals T1 plus T2 by 2. Now, in order to consider this bimorph effect, consider a cantilevered beam made out of two different material with different coefficient of thermal expansion. So, on heating both the layers, try to expand differently, but are adhered to each other to the thermal strain. So, the thermal strain is relieved by bending, and the beam given in figure is heated at a temperature of del T. And as there is no external force or moment, the equilibrium equations are P1 equals P2 equals P, P of T1 plus T2 by 2 equals M1 plus M2. Let R be the radius of the curvature of the bend beam, and M1 equals minus E1 L1 by R, and M2 equals minus E2 L2 by R. Now, by representing the free body diagram, this is the free body diagram of the bend bimorph beam. The elongation of the layer have three components: a thermal expansion component, axial deformation component due to a force P, and a elongation component due to bending. Thus, the radius of the curvature of the bending can be determined by, for one, del T plus P by E1 T1 B plus T1 by T2 by R is equal to alpha 2 del T minus P E2 T2 B minus T2 by 2 by R, where alpha 1 and alpha 2 are the coefficient of thermal expansion of bottom and top of the layer, since because these two are kind of an heterogeneous structures and these two are participating in the overall actuation. In fact, when we have seen the earlier video with reference to SMA bimorph based actuation, so we have seen that the SMA, when it tries to deflect, there is the actuation is happening on the SMA. Similarly, when we try to bring it in an open environment, it comes back to its shape because of the participation of the polymer. So, ideally, both the coefficients of thermal expansions needs to be taken up into consideration, and E1 and E2 are the Young's modulus of top and bottom layers respectively, and T1 and T2 are the thickness of top and bottom layers respectively, and B is considered to be the width of the beam. Now, the transverse load, let us consider the effect of residual stress in this particular case. So, since we had two different composition or two different heterogeneous layer, when there is an actuation exhibits, ideally it may result in a kind of a residual stress within the system. So, in fact, when we try to study the overall failure or the degradation behavior of any such kind of this shape memory alloy structures. So, one of the key aspect which comes into mind is like whenever we are trying to study the degradation behavior of shape memory alloy bimorph or the shape memory alloy structures. So, one of the key aspect which comes into mind is like when we are trying to integrate these two structures, when there is a continuous movement which happens, this will end up in a certain amount of like residual stress in these particular layers. These residual stress will slowly build up, it will result in a hysteresis, and then there will be a kind of a reduction in the overall performance of this shape memory alloy structure or of these bimorph. So, this is quite evident for all kinds of bimorph which are being used functionally. So, appropriately certain amount of preconditions are deployed so that to take care of this residual stresses. Either in some cases what people used to do is people used to strain the film after it is getting deposited, or in certain cases what people used to do is people used to use a kind of a pre-straining as well as a heating condition to take care of such kind of residual stress. So, those things we will be discussing in the upcoming lecture.